combination with 4 for problem 52A. Of course, to work it out the long way, you'd have 96 factorial over 4 factorial times 96 minus 4 factorial. But, ladies and gentlemen, we have this function at our disposal on our calculator, and so feel free to use it. 96 in combination with 4 gives you, as you would guess, quite a few arrangements here. So looks like 3,321,960 different ways of filling the 4 remaining seats on the committee. Okay. Everybody understand that there? All right. So we're going to be a while trying to fill these 4 seats. All right. All right, that's 52A. Now, 52B, in how many ways can a group of 3 U.S. senators be selected from a group of 7 senators to fill the positions of chair, vice chair, and secretary for the ethics committee? Now, for this problem here, do you think order matters for a problem like this? All right, we're trying to fill these 3 different offices, chair, vice chair, secretary. So order will matter. And in this case, we're going to have to use a permutation. So it's going to be 7 permuted 3 ways for 52B. 7 permuted 3 ways. And let's get on our calculator and dial that up. All right, so 7 permuted 3 ways. What's that going to give us? Well, that's going to give you 210 different ways here to fill these seats here. And of course, these seats do have, different designations. So that's why order matters here in this situation. Okay. All right, these problems making sense so far here? All right, problem number 1, like number 56. In the New York State Lottery game, Lotto, a player wins the grand prize by choosing the same group of 6 numbers from 1 through 59 as is chosen by the computer. How many 6-number groups are possible? Now, does anybody play the Lotto? Because I don't. Anybody out there? Anybody play the Lotto? Well, does anybody out there play the Lotto? Can anybody hear me? Am I on the air or what?
I just don't.
Okay. I don't think the order in which you have these 6 numbers on your ticket matter. Somebody out there, correct me if I'm wrong.
Oh, but for the like that, yeah, the order does matter as far as I know.
The order does matter. Though. Wow.
I can look it up.
That makes it even tougher if the order matters, because it's hard enough just to get all 6 numbers. Do you agree? Let alone put them in order. Oh my, really? Order matters? I guess if I had to guess, I would think that order probably doesn't matter, but if it does, that's going to make the game a little tougher. All right.
I looked it up. The order does not matter.
Order does not matter. Okay. Yeah. I mean, in my thinking, I think it's tough enough just to get the 6 numbers. Now, that in of itself, as we're going to find out, the number of possible arrangements is very difficult. Let alone ordering that would be horrendous. All right. Anyways, order does not matter. So we have 59 numbers to choose from. Correct. All right. Now, 59 numbers to choose from, and we have to put together, get the same 6 numbers the computer chooses. So, so therefore, we're going to have, for problem 56, we're going to have 59 in combination with 6. And let's get on our calculator and dial that up. And that gives you a whopping number. That's 45,057,474 different arrangements of 6 numbers from 59 numbers. And now, if order mattered, that would be a permutation. Whoops, that would be a permutation. And it's just for the sake of the argument here, let's see what the difference would be here. Yeah, there's going to be a difference here. It's going to be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 2, 4, 4, 1, 3, 8, 1, 2, 8, 0. This is if order mattered, if you had to get the 6 numbers in a specific order to win. This would be 324,441,381,280 different arrangements if order mattered. You could see your chance of winning if order mattered would be almost literally non-existent. Okay. There's a small chance, don't get me wrong. But ladies and gentlemen, the probability, to give you a snippet of where we're going in the last section of this course, the probability of getting the correct ticket, there's only one correct ticket out there with all 6 possible numbers on it. And for us to get that ticket, the probability is going to be 1 divided by this huge number here. And so 1 divided by is very small. Let's see, 1, 2, 3, 4, 5, 6, 7, 2, 2. And if you multiply it by 100%, that's only going to take away 2 of the zeros here. That's your percent chance of winning this thing. That's your percent chance. Now, 1% is way up here. That's the 1% position here. And so this is small. Tenths, hundreds, thousands, tens, hundreds, thousands, 10,000s, 100,000s, million, 10 million. So you have 22 10 millionths of a % chance of winning this lotto. 22 10 millionths of 1% chance of winning this lotto, of getting all 6 numbers correct. You can see that the percentage is way down there. And because of that, I'm probably not missing anything if I forego playing the lotto. All right, very, very slim. But as that movie, that line in that movie says, but wait a minute, you're saying there's a chance, right? You're saying there's still a chance. Yeah, there's a chance. But like I said, you probably have a better chance of getting run over by a turnip truck walking across the street. All right, number 58. A committee of 4 men and 4 women is to be made from a group of 12 men and 9 women. In how many ways can such a committee be formed? So we have 12 men to choose from, 9 women to choose from, and we have to put together a committee that has 4 men and 4 women. How many different such committees could be arranged? Well, order does not matter here, ladies and gentlemen, because we're just trying to, select 5 guys and 5 women, ladies. Okay, so order just doesn't matter. So we ask ourselves, how many different arrangements or how many ways can we select 4 men from 12 men? That would be a combination. So 12 in combination with 4 would be the total number of ways of selecting 4 men from 12 men. And we have 9 women, and we need to select 4 women from 9 women. And we use the fundamental principle of counting because we have to have 4 men and 4 women on the committee. So this is the number of ways of forming a committee of 4 men. This is the number of ways of forming a committee of 4 women. Therefore, we must multiply these together to get the total number of committees that can be formed, okay, with these requirements. So 12 in combination with 4. We're going to take that. You know, you might have to enclose these inside parentheses in your calculator if you type it all in on one line. I would probably do that just to be safe. It doesn't hurt. So let's, just make sure that you can do this on your calculator. And when all is said and done, you should get 62,370 different ways of putting together a committee of size 8, where 4 have to be men, 4 have to be women, if we have 12 men to choose from and 9 women to choose from. Okay. All right. So that's using the fundamental principle of counting there. So it's using combinations and the fundamental principle of counting. All right. Okay. Let's see what else we got here. Problem number 74. Consider the set of numbers 0 through 5. How many, the set of integers 0 through 5, how many 3-digit codes can be formed with the given restrictions in 74? The code may not contain repeated digits. So we cannot have repeated digits here. And so what are we going to do here? Well, one way to kind of look at this problem is to think of us having like 3 mailboxes that have to be filled here, or 3 slots that have to be filled. And we're going to choose from the numbers of 0, 1, 2, 3, 4, and what was it? It was up to 5, I believe. Okay. Up to 5. So how many of these numbers can occupy the first slot? Well, that would be 6. But we got to leave one of the numbers out and keep it in the slot because we cannot have any repeats. So we only have 5 remaining to fill the second slot. But we got to keep another digit out. That means we reduce our lot down to 4 digits left to select to fill the third slot. And the fundamental principle of counting is going to have us multiplying all these together. So there would be, it looks like 120 different codes of size 3 where there's no repeats allowed. Now, another way to deal with this is to think of this as being a permutation because order does matter with this code, correct? Now, for instance, the code 1, 2, 3 is not the same as 3, 2, 1. Now, when it comes to codes, okay, passwords or codes, order does matter. So this would be like a permutation. So we got 6 numbers permuted 3 ways. And therefore, if we dial this up, and we will see that we get the same number. Now, if you want to compute this manually, it would be 6 factorial over 6 minus 3 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And 6 minus 3 is 3 factorial. So 3 factorial is 3 times 2 times 1, but the 3 times 2 times 1 cancels, and it leaves you with 6 times 5 times 4, and that's precisely what we have here. Okay. All right, so that is a permutation for that problem there. All right. So, any questions about any of these here? Good, number 80 here. Social Security number is assigned number 80. Social Security numbers assigned in the United States are comprised of 9 digits of the form 3 digits dash 2 digits dash 4 digits. Would there be enough Social Security numbers for the population of China? If the Chinese use the same system, population of China is approximately 1.5 billion. Okay, so ladies and gentlemen, can we have repeated digits in a social security number? Yes or no?
Yeah.
I believe we can. All right. So therefore, we have to fill how many slots? We got 3, 4, 5. We got nine slots, correct? All right, 9 slots. So is this going to be a permutation or combination? Does order matter in which you list these digits? Yes or no? Do you think so? Or I think order matters, doesn't it? In other words, the first 3 digits of Social Security number 371 is different than 173, which is different than 137. Okay, so order does make a big difference. So I'm thinking permutation. Therefore, permutation would be the way to go here. So how many slots? Let's see here. How are we going to do this problem here? Permutation maybe or not? All right, so how many digits do we have to choose from here?
9.
Let's see. Well, we got 0 to 9.
10 digits, 9 slots.
10 digits, 9 slots. So one way to think of this problem is to think of it as, having 9 slots here. 3, 4, 5, 6, 7, 8, 9, and we got 10 digits to assign to each slot. So using the fundamental principle of counting, it's going to be 10 times itself, 9 times. This is going to be 10 raised to the 9th power, which is really 1 billion. Okay. 10 to the 9th power is 1 billion. So I think if the Chinese used this system, they would run shy. They would not have enough numbers to go around here, because if their population is 1.5 billion, that's 1,500,000,000 people. So 500 million people would not have any social security number. Okay. So definitely it looks like they would have to adopt some other system, or maybe they might have to add maybe an extra digit or so. Do you agree on the social security number? So that might circumvent it. All right, so that's the end of section 8.6. Section 8.7 opens up what's called basic probability, or introduction to probability. You can go deeper into the world of probability if you take statistics and probability here at Math 150. It's an awesome course, very, very useful, especially when it comes to data analysis. If you're going to work with any data out there in the real world for any company or any business or for any research purposes, it is strongly advised that you take a course in statistics and probability. Even computer scientists should take a course in probability and statistics. Reason being is because if you go into computer programming or software engineering or design, there's times when you're going to have to tap into methods of counting, and you're going to have to teach a computer how to count, okay, by programming combinations or permutations into the code. That's just one snippet of where probability and statistics comes into play in computer systems. Right? Okay. And modeling data by collecting data out in the field and modeling it according to a linear relationship or quadratic or trigonometric or logarithmic relationship involves regression analysis, and you study regression in statistics. Okay. All right. Section 8.7, intro to probability. Okay. Now, in order to be efficient in the study of basic probability, we need to arm ourselves with a little bit of terminology so we can speak the probability language. All right. So when we work with probability, ladies and gentlemen, we often think of probability as kind of like the likelihood that a particular outcome will occur. And we speak in terms of probability all the time. You hear it on the media, like what's the probability of snow tomorrow? Well, in large part, that depends upon what the high temperature is going to be tomorrow, because if the high temperature tomorrow is 75 degrees Fahrenheit, then the probability of snow is like 0%. Do you agree? Because the temperature regime is not even conducive to support snow. So you can get into what's called a conditional probability. Given tomorrow's high temperature is only going to be 29 degrees Fahrenheit, then do you agree there is a probability that you could potentially have snow? But does that mean it's gonna snow just because your high temperature is 29 degrees Fahrenheit? No, it could be a sunny day with a high temperature of 29 degrees. All right. So, but nonetheless, we speak in terms of probability. I like to think probability is where probability picks up, ladies and gentlemen, where mathematical certainty leaves off. Okay. There are certain things in everyday lives or certain phenomena whereby we do not understand them well enough to, with certainty, model them according to a precise mathematical relationship or equation, in which case we must speak in terms of probability. Okay, what's the probability of something being in a particular state, et cetera, et cetera. Right. So when we conduct probability or talk about probability, the first thing that we need to do is conduct some sort of an experiment. And these experiments are a little different than the experiments you would conduct like in a chemistry or physics lab. Typical experiments in probabilistic circles would be like flipping a coin. That could be an experiment, or we could roll a die. Die is singular. Dice means more than one six-sided figure, okay? We could roll a die, or we could basically select a number from an urn. An urn is a container, okay? That could maybe contain slips of paper, each with a number on it, or maybe maybe other objects like balls or something. Anybody play bingo out there? Anybody play bingo? I played bingo once enough to know, ladies and gentlemen, that's just not for me. I'm no good at it. I am convinced if I was the only person playing bingo left on planet Earth, I could still not win. Okay. So I shy away from bingo. Now in bingo, I am told that you got a bunch of balls bouncing around in the container and one is randomly selected. Okay, so each ball is understood to have an equal chance of being selected. All right, so these are examples of experiments that could be conducted in probability here. Now, when you conduct an experiment, there has got to be some sort of an outcome from your experiment. All right. And for the example, when you flip a coin, there's going to be two possible outcomes. And we also, therefore, like to form what's called a sample space, which basically gives us a listing of all the possible outcomes of a particular experiment. So the sample space for flipping a coin would be the set consisting of a head or a tail. Right? Those are the outcomes that could occur when you flip a coin. All right. When you roll a die, the sample space would be a set consisting of 1, 2, 3, 4, 5, and 6. Okay? That's rolling a die. All right. And then we need to indicate what an event is in probability. An event is a collection of two or more outcomes of a particular experiment. Right? So like when you roll a die, an event, and we always use uppercase letters to represent events. So I could define event E to be the event that we roll an even number on a die. Okay, that would be an example of an event. Sometimes they use subscripted variables. For instance, E sub 2 could be an event defined to be maybe that we roll an odd number on a die. All right, so they always use uppercase letters to represent events, and that's not just our textbook. That's pretty much universal from stat book to stat book. Okay, so that's a convention that's used. All right, then we can start to get into the probability symbolism or notation. And so if we see this notation, we should know what it's saying and how to read it. This notation is to be read as the probability of event E occurring. Okay. That's the probability of some event E occurring. That's how you read that notation. And we are going to show ourselves how to compute probabilities. All right. Now, there are two main ways of computing probabilities. First of all, any questions about any of this lingo here? All right, there are two main ways for computing probabilities. The first model, if you will, or method is called the equal likelihood model. And that is basically saying that each outcome of an experiment, whatever the experiment is, has an equal chance of occurring on any given trial of the experiment. Okay. All right. So suppose that we look at the experiment of flipping a coin, a fair coin. Now, what does it mean for the coin to be a fair coin? Anybody want to weigh in on that?
Is it an equal likelihood of landing on either side?
Yeah, to say that we have a fair coin means the coin is not weighted in any way, shape, or fashion, and so that that affords the chance, if you will, or the probability of a head occurring as being equal to the chance or probability of a tail occurring on any given flip. Now, technically, I mean, the door is left ajar for the possibility of a coin landing on edge when you flip it. I've never seen that happen, although it's not, technically impossible. The probability is so darn small of that occurring, and that you just don't, you don't experience it. If you ever flip a coin, ladies and gentlemen, it hits the table and lands on edge, please make sure you get a video or a picture of that and put it on YouTube or something so we can all enjoy it. All right. And so I know somebody out there is going to start flipping a coin tonight and burn the midnight oil, flipping it about 1 million times tonight, right? Trying to have that duplicated. I wouldn't recommend doing that. Could be a while. All right. Anyways, what's our sample space? Our sample space consists of two possible outcomes for all practical purposes. Practical purposes, we say there's only two outcomes, head and tails. Like I said, we're not going to entertain the possibility of it landing on edge here. So suppose I define event E to be that we flip ahead. So therefore, what would be the probability of event E occurring? Well, we're going to use the equal likelihood model for computing this probability. The equal likelihood model has us taking the number of ways that the event can occur and dividing it by the total number of outcomes that exist in the sample space. All right, this is called the equal likelihood way of computing probabilities. So the probability of flipping a fair coin and having it come up heads, how many ways can a coin yield a head? That's only one way. Out of how many possible outcomes in the sample space? There's two, and so you got your probability. So the probability of flipping a head would be 1/2. Now, normally we leave probabilities as reduced fractions. You can represent them as, you know, decimals. I mean, there's nothing that says that that's illegal. But just for the record, this is very important note. When you compute the probability of some event occurring, while conducting an experiment, probabilities must always be decimals or fractions that lie between 1 and 0 inclusive. Okay? In other words, you're never going to compute the probability of some event occurring and it be like 2 or 3 or -1 or -2. That's impossible. Probabilities are always decimals or fractions between 0 and 1. If the probability of some event E occurring is equal to 0, then we would say that E is what? Impossible and never will happen. Okay. If the probability of some event E is equal to 1, we would say that E is what? Certain to happen, correct? Will happen. It's a guarantee, it's a given. All right, there you go. I know one event that's certain to occur. We all have to pay taxes. What's the probability we have to pay taxes? 1. It's equal to 1. Okay. All right. So that's a certainty there. So again, ladies and gentlemen, probabilities are always decimals or fractions between 1 and 0 inclusive. Right? Never are you going to compute a negative probability or a probability that's greater than 1. Of course, in our minds, we know a probability equal to 1 would be 100% chance, 0% chance. 1/2, which is 0.5. In our minds, we know it to be 50%, but we don't represent probabilities as percentages. We leave them as fractions or decimals. Okay. All right. Suppose that, so that's the equal likelihood model. Any questions about this here? Equal likelihood. Suppose that we have a container or a box, or if you want to call it an urn, you can call it that also. And in this container, we have, let's say, 4 green balls. We have 2 red balls, and we have 3 blue balls. Okay. All right. So what's our sample space? Our sample space consists of 4 green balls, and we could maybe call it green ball number 1, 2, 3, 4. 2 red balls, red ball number 1, red ball 2, 3 blue balls, blue 1, blue 2, blue 3. Okay. So this would be the sample space for the experiment of reaching in and pulling out a ball. Now, in order to ensure that each ball has an equal chance of being selected, we would have to randomize these balls. And what does it mean to say we're going to randomize the balls? Well, to randomize all these balls means that we're going to what? Thoroughly make sure that they are mixed up, okay? To the point where any one of these balls has an equal chance of being selected. All right, suppose that I define event E to be the event that a red ball is selected. And therefore, what would be the probability of event E occurring? Well, it's going to be the number of ways that event E can occur divided by the total number of possible outcomes that are in the sample space. So how many ways can we select a red ball? Well, there's 2 different ways. Divided by how many different ways can we select the ball from this container? There's 9 different ways, correct? So that would be the probability of selecting a random ball, or excuse me, a red ball when the balls have been randomized. Any questions about that there? All right, suppose I define event A to be that we select a white ball. Ladies and gentlemen, what would be then the probability of event A occurring? Well, that's going to be equal to the number of ways that event A could transpire divided by the number of possible outcomes in the sample space. Now, how many ways can we select a white ball from this container? Well, there are no white balls, so there's 0 ways to select a white ball, and therefore it'd be 0 divided by 9 or 0. That's the probability of selecting a white ball from this container. Oh, we're assuming the person conducting this experiment is not colorblind. that might come in handy too. All right. All right, so is this making any sense so far here? Basic probability. Okay, let's go to our book. I want to show you something. Let's see. So section 8.7 is probability here. All right. Suppose that we roll 2 dice, okay, and we want to find some probabilities. So when we roll 2 dice, and by the way, this is example 3 in your textbook, section 8.7. When you roll 2 dice, how many different outcomes are possible as far as the numbers are concerned? Well, the labeling of the columns represents the number that shows up on the first die, and the row designation is the number that appears on the second die. Notice you could roll your 2 dice and get the first die showing a 1, the second die showing a 1, or the first die showing a 2, and the second die showing a 1. Just because, I mean, look at these coordinates here. Notice the first coordinate pertains to the second die's outcome. The second coordinate pertains to what transpired on the first die. So just be careful of that. Anyways, ladies and gentlemen, there's 6 ways or 6 outcomes from die 1 and 2. So there would be 6 times 6 or 36 different possible outcomes that could occur when you roll these 2 dice. And suppose we were interested in computing the probability that the sum of the numbers showing on the dice amounts to or adds up to 7. That would be equal to the number of ways that 7 can occur. And how many different ways can 7 occur? In other words, if I define event E to be that we roll a sum of 7, then event E can occur 1, 2, 3, 4, 5, 6 different ways, correct? If we roll a 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, or 6 and a 1, the sum of those die, those faces is 7. So there's 6 different ways in which we could roll a sum of 7 divided by the total number of outcomes that could occur when you conduct this experiment, which would be the size of your sample space, which is 36. So the probability of rolling a sum of 7 would be 1/6, which is about 16, almost about 17% chance. Okay, but we leave it as a fraction, 1/6. All right, B, what's the sum? The probability that the sum of the numbers showing on the dice is not 7. I am going to get to that in a moment, so I will come back to that that concept there. Okay. All right, so we'll revisit that when I explain something else that we need to know. All right, so one way to compute probabilities is to use the equal likelihood model, which is assuming that each outcome of an experiment has an equal chance of occurring. Okay, that's the key assumption. All right. What if, however, ladies and gentlemen, each outcome of an experiment does not necessarily have the same chance of occurring? If that's the case, then we would have to use a different way of computing probabilities. And the second method is known as the relative frequency method. So the relative frequency, or they sometimes call it the empirical way of computing probabilities. Okay, and what way is that? Well, to compute the probability using the relative frequency or the empirical way. So to compute the probability of some event E occurring, it's going to be equal to the number of times event E has occurred in the past divided by the total number of trials of an experiment. This is called the the relative frequency or the empirical method for computing probabilities. All right. So for instance, here's an example. Suppose that I take, let's say, 20 shots at a basket, okay? Basketball here. Let's suppose I make, let's say I make 12 shots. So then, ladies and gentlemen, what would be the I could form an event. Suppose I define event E for this experiment of shooting the ball to the basketball, the basket, the hoop. Suppose event E represents the event that I make a shot, okay, on any given toss to the basket. Well, the probability of event E occurring is going to be computed by using this relative frequency model here, which is to say that it would be the number of ways that event E can occur in my situation. In other words, how many times has event E transpired in the past? Well, I made 12 baskets in the past, divided by how many trials for this experiment? Well, I took 20 shots at the basket or the hoop there. And there you go, ladies and gentlemen. That would be the probability that I make a shot whenever I toss a basketball at this basket or this hoop. You can reduce that down by 4 down to 3/5, and that would be the probability that at any given time or trial I shoot this ball to the basketball hoop, that I will have about a 60% chance of making a basket. Okay. So this is the relative frequency way of computing probabilities. Now, there is a law in the world of probability called the law of large numbers. And this is saying as the number of trials of an experiment approaches infinity, okay? In other words, if I was to sit here for the rest of my life shooting balls at this basketball hoop, okay, then we would say for all practical purposes, the number of trials or shots I'm making at this basket is approaching, for my purposes, my lifetime is, we might as well call it infinity, all right? The law of large numbers in probability says as the number of trials of an experiment approaches infinity, then this law of large numbers says that relative frequencies tend to approach true probabilities. Okay. So relative frequencies tend to approach true probabilities. And so that can be experienced if you toss a fair coin. Let's say you toss a fair coin like 10 times, okay? 10 tosses of a fair coin. And does that mean, ladies and gentlemen, that you're going to toss exactly 5 heads and 5 tails when you toss a coin 10 times? Does that imply that? Do you think you're necessarily going to toss 5 heads or 5 tails when you toss a fair coin 10 times? You could, right? It's possible, but you may not. But I guarantee you that if you continue to toss this fair coin for more and more and more and more number of trials, so if you allow the trials to increase, so like if you toss this coin 1,000,000 times, I guarantee you that the relative frequency of the number of heads that you toss is going to approach the probability of a head occurring on any toss, which we know would, for a fair coin, would be 50% chance, 0.501 half, okay? So just because you don't toss, 5 heads out of 10 tosses on a coin for a fair coin, doesn't mean the coin's not fair. You got to realize that in order to experience the fairness of the coin, you would have to toss the coin for a larger and larger number of times. And I guarantee you, if you do that and kept track, you would see then that the relative frequency of occurrence of heads would approach the true probability of what we would expect for a fair coin to be 1/2 or 0.50. Okay, that's called the law of large numbers. Okay. So we got the equal likelihood model if each outcome has an equal chance of occurring, and we have the relative frequency model way of computing probabilities. The next thing we need to arm ourselves with is called the complementary probability rule. And the complementary probability rule is saying this. If events A and A bar are complementary events. Now, I'm going to have to define or give you an example to illustrate what it means for events to be complementary. So just hang on for that for a moment. If A and A bar are complementary events, and this is the notation that's used in your textbook to represent that this event is complementary to event A. They use a bar over it. If these are complementary events, then, ladies and gentlemen, it is true then that the probability of event A occurring plus the probability of its complementary event occurring must always be equal to 1. Okay, this is called the complementary probability rule. That's always true. Okay. Now, what are some examples of events and complementary events? Well, suppose I define event A to be that a light bulb is on. So what would be the complementary event of a light bulb? What do you think it would be?
Would it be the light bulb being off?
That is correct. The complementary event for event A, based on how event A is defined, is to say the complementary event would be that the bulb is in the other state, which means that the light bulb is in the off position. Okay. There's no in between with a light bulb. I mean, it's not, partially on, off, on. No. A bulb's either on or it's not on. It's either on or it's off. Okay. These are called complementary events. Suppose I define event E1 or E sub 1 be the event that I roll an odd face on a die. What would be the complementary event to this event? What would it be? So the complementary event of rolling an odd face on a die would be that I roll a what? That I roll an even face on a die. All right. These are complementary events. Suppose I define event A to be that I select I select an ace from a deck of cards. What would be the complementary event? Complementary event would be that I what? Do not select an ace from a deck. All right, listen to this one here. Suppose that a string of lights, since this is the season for putting up lights, suppose that a string of lights has 1,000 bulbs on it. Okay. Suppose I define event E1 to be the event that all 1,000 light bulbs work. What would be the complementary event, which I'll call E2?
Would it be at least one of them doesn't work?
That's exactly right. Ladies and gentlemen, the other side of the fence of saying that all 1,000 light bulbs working are going to work on a string of lights is to say that at least one of them is not going to work. At least one of them is going to burn out. Okay. So at least one bulb fails. Now, that's to say that, you know, maybe one bulb fails, or maybe two bulbs fail, or three bulbs fail, or four, or maybe all 1,000 fail, but at least one of them must fail. Okay, that would be the complementary event in that situation. So complementary events are kind of like the other side of the fence, you know. If event A is that a respondent, well, I can't use that there. Okay, so we can't do that. You know, computers are kind of like complementary machines in a sense. They got a bunch of components that are either in a high voltage state, or if they're not in a high voltage state, they're in a low voltage state. We know those better as zeros and ones, binary code that computers basically operate on. We view them as zeros and ones, but computer componentry views them as high voltage states versus low voltage states. Okay, that's how computers operate. They use a bunch of little gates on board called, you know, different various gates, NAND gates, NOR gates, OR gates, AND gates. All right, a whole bunch of digital logic is occurring on a computer system, and it's basically a high voltage state versus a low voltage state. So computers are a binary machine, to say the least. All right. So gates are kind of like complementary, or states on a computer are complementary outcomes. All right, so let's go back to our textbook now. Wait a minute here. Yeah, okay. I got to share my screen. What am I talking about? All right. So let's try to go back here. Now, ladies and gentlemen, let's go back to rolling two dice, okay? There's 36 possible outcomes. Of course, we already computed probability of rolling a sum of 7. That would be, what, 6 over 36, or 1/6? What would be the probability of rolling two dice and the sum not being 7? Well, the tough way of doing this problem is to count up all the outcomes that do not yield a sum of 7, but there's an easier way. And the easier way is to use the complementary probability rule, which can save you a ton of times in certain situations. So the probability of not rolling a sum of 7 is going to be equal to 1 minus the probability that we what? The complementary event of not rolling a sum of 7 is to say that what? We roll a sum of 7. And we already computed the probability of rolling a sum of 7. It's 1/6. So 1 minus 1/6 then would be the probability of not rolling a sum of 7, which is to say 6/6 minus 1/6, which is to say 5/6, then would be the probability of not rolling a sum of 7. Okay, so this complementary probability rule, ladies and gentlemen, can really save our behind. Let me show you another example where it really comes in handy. Remember that string of lights where we have 1,000 light bulbs on it? Okay, suppose that I tell you that the probability of a let's say the probability of all 1,000 bulbs working properly, suppose I indicate that probability is like 0.996 or something, okay? Then, what then would be the probability that at least one bulb fails? Well, do you agree to say at least one bulb fails is really the complementary event of saying that all bulbs function properly, that none of the bulbs fail, okay? And so we can use the complementary probability rule to compute this. So it's just going to be nothing more than 1 minus the probability that all 1,000 bulbs work. And so therefore it'll just be 1 minus 0.996, which is going to give you 0.004. So there's the probability at least one bulb would fail, okay? Which, you know, thankfully is, I just made this example up. I don't know if that's a true probability for a string of lights or not. I just, you know, made this up for illustrative purposes, but fortunately the probability is pretty low, correct? I swear though, for my Christmas lights, my string of lights, the probability is more like, what's the probability that one light's going to fail, or one bulb's going to fail? It's more like this for my lights. I don't know about yours. Hopefully it's not.
I was
that bad.
about to say, shouldn't they be swapped?
Yeah,
That's more
yeah.
realistic.
For mine, it's more like this is the probability that at least one bulb is going to burn out. Yeah, because that's the way it always works. Never fails. Okay, so that complementary probability rule can, you know, like I said, it can spare us a lot of headache in computing various probabilities. So just try to remember that complementary probability rule. And, you know, you could solve this equation for any one of these unknown probabilities because we know this is true. So like you could solve for the probability of event A occurring, which is going to be equal to like 1 minus the probability that its complement will occur. Or the probability that a complementary event will occur is 1 minus the probability that the original event A will occur. So, you know, these are all synonymous equivalent forms of each other there. Okay. All right. Now here's an example. And I made this in my notes here. Suppose that 5 graduates from college A and 4 graduates from college B apply for 3 job openings. And we're going to assume that all of these graduates, ladies and gentlemen, are equally qualified for these jobs. We will assume that to be the case, you know, just for the sake of argument here. Suppose I want to compute the probability that all jobs are filled by college A grads. Okay, so suppose that given this situation, what then would be the probability that all jobs are filled by college A graduates? Okay. Okay. So that is the question we're going to try to answer here, or the problem we're going to try to address here, all right, computing this probability. And like I said, we may have to go back or revert back into our previous section in methods of enumeration or counting, all right, in order to determine the number of ways an event can occur versus the number of ways a sample space can occur for a particular experiment. So the counting methods do come in handy in computing various probabilities. That's why that section precedes this section. All right. So that's the problem we're going to try to address here. And let's see if we can get a handle on how to navigate that problem here. Okay, so what I'm going to do here is I'm going to let E, the event E, be equal to the event that 3 college A grads are selected for these jobs. Okay. Well, the number of ways that event E can occur would be what? Well, we have 5 graduates from college A, and how many different ways can we choose 3 graduates from college A if we have 5 to choose from, where order does not matter? So this is definitely going to have us working with a combination. So 5 in combination with 3. And keep in mind that these combinations symbolically could also be illustrated this way. So these are saying the same thing, okay? And so 5 in combination with 3 is the number of ways that event E can occur. And what would be the number of ways or the number of outcomes we could get for this entire experiment here? Well, we have 5 graduates from college A and 4 graduates from college B. So totally speaking, how many grads do we have to choose from? Totally. Well, we got 5 from college A, 4 from college B. So we got 9 different graduates to choose from. So how many different ways can you fill 3 job positions if you have 9 graduates to choose from where order does not matter? Well, that's going to be 9 in combination with 3. All right. Or could be represented this way. So therefore, the probability that all 3 jobs are filled by college A graduates is equal to the probability that event E occurs, which is equal to the number of ways that event E can occur divided by the total number of ways of filling these 3 jobs, or the total number of possible arrangements for these 3 jobs in the sample space. And so we're basically just going to take 5 in combination with 3 and divide it by 9 in combination with 3, and this will crank out our probability. Okay. So therefore, we're going to have 5 combination with 3, which is 10. And that's going to be equal to 9 in combination with 3. The 9 in combination with 3, which is 84. And so you can reduce this if you want down to 5 over 42. Now, for interpretability in our minds, you can actually take 5 and divide it by 42 if you want to, and turn it into an approximate decimal. So that's approximately about a 12% chance. So there's about a 12% chance that these 3 jobs are going to be filled by college A grads. Okay. Is that making any sense there? Now, what if I changed my event? I said, if I said event E is that 3 college B grads are selected for these jobs? Would you suspect that probability is going to be higher or lower than what we got here, which is about 12% from college B? What would be your guess? Higher or lower? Well, since there's fewer graduates to choose from college B, then we would suspect this probability is going to be lower than the first probability we computed. And that would be the case. Okay. All right, let's go to example 5 in our textbook here. All right, let's look at example 5. All right. So data from the Centers for Disease Control for a recent year indicate that there were approximately 4,295,000 individuals of age 20 in the United States. 1 year later, 3,887 of these individuals had died, and 4,291,113 had lived. Determine the probability that a 20-year-old will survive to age 21. Well, we will represent event E to be that a 20-year-old lives to be of age 21. And we are assuming that each one of these 20-year-olds has an equal chance of survival. And therefore, we will use the equal likelihood, or excuse me, we're not going to use the equal likelihood model. Actually, we're going to use the relative frequency way of computing this probability based on past, past data. And so of the 4,295,000 20-year-olds that were surveyed, how many survived? Well, you'd have to take the number that passed on and subtract that from 4,295,000, which means there would be 4,291,113 that survived. So you'll take the number of survivors and divide it by the total number of 20-year-olds surveyed, and that would be the probability of a 20-year-old making it to their 21st birthday, which is fortunately a very high percentage, 0.9991. Okay. So I guess that puts credibility into the phrase, when we're young, we think we're going to live forever, which is, nothing wrong with that. That attitude starts to change a little bit when you start to put years on, ladies and gentlemen. I don't want to scare you or anything, but you start to realize your mortality when you get a little older, and it's harder to get out of bed in the morning and all that stuff. Okay. All right. Any questions about probability so far here? Okay. Another thing is a deck of cards. Now, whenever I go over this probability, I never assume that all of us, have played with a deck of cards before. I would imagine that most of us probably have, but there's always that possibility that there's somebody that just hasn't done that. For that reason, I'd like to go over very quickly what we consider to be a standard deck of cards for computing probabilities. And this is considered to be a standard deck of cards. Notice we have 4 different suits, clubs, spades, hearts, and diamonds. And in each suit, we have 13 cards, an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a jack, queen, and king. The jack, queen, and king are referred to as face cards, okay, because they have faces on them. There's 13 cards per suit, so 13 times 4 suits, 13 cards per suit times 4 suits yields 52 cards in a deck. Now, some decks of cards actually have jokers in them, but we are not going to worry about the jokers, ladies and gentlemen, as we will assume a standard deck does not have jokers. Okay, so that is a deck of cards there. All right, does that make sense there so far? Now, if I shuffle this deck, randomize it, which means I thoroughly shuffle it, what would be the probability that if I reach in and pull out a card at random, what would be the probability that I select the Jack of Hearts card? Well, how many ways can the Jack of Hearts card occur? Well, there's only one Jack of Hearts card present in a deck. So it would be 1 divided by how many different outcomes could occur. There's 52 cards that could be selected. So your probability of selecting the Jack of Hearts Jack of Hearts card would be 1/52 using the equal likelihood model, assuming your deck has been thoroughly randomized and shuffled, okay, which means thoroughly shuffled, okay? All right, is that making any sense so far here? Okay. Okay, I'm gonna go down here and, well, I'll tell you what, I think we best just keep moving right on here. Okay, I'm going to show you a couple of rules of probability. I already showed you the complementary probability rule. I'm going to show you some addition rules of probability. Okay, all right. In order to understand these addition rules for probability, we need to understand what it means for 2 or more events to be mutually exclusive or disjoint events, okay? All right, so here's kind of like a definition here. To say events A and B are mutually exclusive, or disjoint, depends on what textbook you look at as to how they coin these, mutually exclusive or disjoint events means that both events A and B cannot, okay, occur on any, cannot occur at the same time on any trial of an experiment. All right, so that's what it means for 2 or more events to be mutually exclusive or disjoint. They cannot occur at the same time on any given trial of a particular experiment. Okay. So some examples here of mutually exclusive or disjoint events. Suppose my experiment involves, let's say, flipping a coin. Suppose I define event A to be that I flip a head. And suppose I define event B to be that I flip a tail. All right, these are complementary events we've already seen, but ladies and gentlemen, we would also call these events disjoint events. Or we would say they are mutually exclusive events in the sense that when you flip a coin, you cannot have both these events occur simultaneously on any given trial or flip of the coin. You're either going to flip a head or a tail. There's no flipping a head tail or a tail head or something like that. Okay, it's either a head or a tail. There's no both of these happening. These are called mutually exclusive or disjoint events. All right. Any questions of what it means for events to be mutually exclusive or disjoint? They cannot occur at the same time on any given trial of an experiment. So if I define event A to be that a light bulb is turned on, event B to be that the light is off, notice those events would be mutually exclusive or disjoint. When we observe the light bulb, both events cannot occur simultaneously. You cannot have a light bulb that's partially on, off, or off, on. It's either off or it's on. Okay. All right. So here's our first probability rule here. If events A and B are mutually exclusive. So if we have two or more events that are mutually exclusive, then, ladies and gentlemen, we say the probability of event A or event B occurring, or is called a disjunctive word in mathematics. A disjunction suggests the union between sets, the joining of sets together. So your author, instead of using the word or, has a tendency to use the union symbol. This means the same thing as the word or, though. Okay. So the probability of events A or B occurring on a given trial of an experiment is going to be nothing more than the sum of the individual probabilities. So it's going to be equal to the probability of A occurring plus the probability of B occurring. This is your first addition rule of probability. That's assuming that the events are mutually exclusive, which means they cannot both occur at the same time. If, however, events A and B are not mutually exclusive, to say they're not mutually exclusive means that they could both occur at the same time on a given trial of an experiment. Okay. Then, ladies and gentlemen, the probability of event A or B occurring is going to be equal to the sum of the individual probabilities, just like a rule above. But then we have to subtract off a very important probability at the end. We have to subtract off the probability that A and B both occur. Okay. This is, I like to call it the general addition rule for probability. This is presupposing that the events can occur at the same time. This is a well-known fact. If the probability of A and B occurring at the same time is equal to 0, then this would imply that events A and B are what? They are mutually exclusive events. If, on the other hand, the probability of A and B occurring is not equal to 0, then that means these two events could occur at the same time. So this would imply that events A and B are not mutually exclusive or disjoint? Meaning they could occur at the same time. Okay. Any questions about what it means for events to be mutually exclusive or not mutually exclusive? And the two different addition rules for probability here. All right, you're probably wondering, why do we subtract off this probability at the end here? This probability at the end has a name. We refer to it as a joint probability. Joint probability. Well, I'll show you. I'll show you an example. All right, suppose we go back to our deck of cards here. What would be the probability if I randomize that deck of cards? What is the probability I reach in and I select a heart or I select a club? Well, ladies and gentlemen, are these events mutually exclusive or disjoint? Suppose I define event E1 to be that I select a heart, and I define event E2 to be that I select a club. So what do you think? Are these events here, are they disjoint or mutually exclusive? So would these events be mutually exclusive or not?
Yes.
Yes, they would be. There's no way when you select one card from a randomized deck of cards that you're going to select a heart and a club at the same time. Okay, those are different suits. So they are mutually exclusive. Therefore, to compute this OR probability, we would just basically add the individual probabilities together. So this would be the probability of selecting a heart or a club. This is going to be equal to the number of ways in which we can select a heart divided by the number of outcomes that are in the sample space for this experiment, plus the number of ways we can select a club divided by the number of ways that are possible in the sample space or outcomes that are in the sample space. The number of ways that you can select a heart would be, there's 13 heart cards in a deck of cards divided by 52 cards total. Number of ways you can select a club, there's 13 ways of selecting a club divided by 52. So this is going to be 26 over 52, which is going to reduce down to what? 1/2, correct? So that would be the probability of selecting the heart or selecting the club when I reach into a deck that's been randomized and pull out a card. Any questions how we did that there? All right. Okay. Suppose that I define event E1 to be that we select a diamond, and suppose I define event E2 to be that I select the ace of diamonds. Are these events mutually exclusive? So if I reach in and pull out a card out of a deck that's been thoroughly mixed up or randomized, could these two events transpire at the same time when I select one card?
Yes.
Yes, they could. Because I could select the what? Wait a minute here. I don't want to say ace of diamonds here. I just want to say ace here. Okay. So suppose I define events E1 and E2 to be these events here. The question now again is, can these events both occur at the same time when I select one card from a deck? The answer is yes, because you could select the ace of diamonds, correct? In which case both events will have occurred. So we say that E1 and E2 are not mutually exclusive. Or disjoint. Or disjoint. That means they can occur at the same time. Okay. Therefore, ladies and gentlemen, what would be the probability of event E1 or event E2 occurring? Well, that's the probability of E1 in union with E2, if you will. You could think of these as being sets. Okay. Set E1 consists of all the diamond cards, ace of diamond, 2, 3, 4, 5, 6, 7, 8, 9, 10 of diamonds, and the jack, queen, king of diamonds. And E2 is the set consisting of what? Ace of spades, ace of hearts, and ace of diamonds, and ace of clubs. All right. You could think of it that way there. So since these events are not mutually exclusive, to compute this OR probability, we're going to add the individual probabilities together. But then we're going to have to subtract off this probability of both events occurring at the same time. Oh, the word and at the end, your author uses the intersection function. Because and is called the conjunction in mathematics. It means the intersection, not the union of sets. So your author may use this notation for that and probability we're subtracting off at the end here. Okay. All right, now, how would I compute the probability of event E1 occurring, of selecting a diamond? Well, how many different ways can we select the diamond? There's 13 different ways. Divided by how many different outcomes are possible when you choose a card from the deck, there's 52 outcomes. Do you agree, ladies and gentlemen, that I counted the what? Ace of diamonds cards in enumerating this first probability? Do you agree the ace of diamonds card was counted among the other 12? Isn't that true? So we counted the ace of diamonds card one time here. Plus, to compute the probability of event E2 occurring, the probability of selecting an ace. Okay. How many ways can we select an ace from a deck of cards? There's 4 ways out of 52 cards. Do you agree in computing this probability of event E2 occurring? I once again had to count the what? The ace of diamonds cards. The ace of diamond card among the other 3 other aces. So how many times did I count the ace of diamonds card in enumerating these 2 probabilities?
Twice.
Twice. But that's a problem because you cannot double count a card. And because of that, we have to subtract off or compensate for having double counted the ace of diamonds card by subtracting off this joint probability f. So what's the probability of selecting the ace of diamonds card, the ace and it being a diamond card? Well, there's only one ace of diamonds card in a deck divided by 52. So this is going to give you the probability of selecting a diamond or an ace when you select a card from a randomized deck. 13 plus 4 is 17, minus 1 is 16. So we got 16 over 52. And we could at least reduce this down by what? By 4, if nothing else. Take it down to 4 over 13. And that would be the probability of selecting a diamond or an ace. Okay. So it does make a big difference if your events are mutually exclusive or are not mutually exclusive or disjoint. And so that's why it's important to understand that. So you use the appropriate addition rule. Okay. Any questions about that there? All right, let's go back to our textbook here. And see, I'm running low on, let's see how the clock is doing here. Oh yeah. Clock is beginning to win the war again. All right. Example 7. This is a good example to look at. The safety and security department at a college asked a sample of 265 students to respond to the following question. Do you think that the college has adequate lighting on campus at night? The table below gives us the responses from 265 randomly chosen students. We had 103 male, 162 female. We had 128 students respond yes, 109 students respond no, 28 students had no opinion. So, ladies and gentlemen, suppose that I want to compute these probabilities. What is the probability that a randomly selected student answered yes or had no opinion? Yes or no opinion? I have a question for you. Since OR separates these events, we're going to be using an addition rule. Are these events mutually exclusive or not? Responding yes or responding with no opinion? Can a student who is randomly selected respond both yes and no opinion simultaneously? That's not happening, agree? All right, so these are mutually exclusive events. Therefore, to compute this OR probability, all we have to do is just add up the individual probabilities. So what's the probability that a student selected responds yes? Well, how many responded yes? 128 out of 265. Plus, what's the probability of picking a student at random and them having no opinion? That would be 28 that had no opinion divided by 265. Therefore, the probability of selecting a student randomly and them responding yes or no opinion would be 156 over 265. Does that make sense there? Okay. For B, what is the probability of randomly selecting a student and then having the student respond with no or was a female? Are these events mutually exclusive or could they occur at the same time on any given trial of this experiment? The trial being the polling of a student at random. What do you think? Could these events occur at the same time? Well, we could select a female that said no. Do you agree? That's definitely possible. So these events are not mutually exclusive. Therefore, to compute this OR probability, we're going to have to use the general addition rule. So to compute the probability of randomly selecting a student and that student saying no, there's not adequate lighting, all right, or that student being a female, we would add the individual probabilities together and then subtract off this joint probability at the end. So the probability of randomly selecting someone and them responding no would be 109 over 265, plus the probability of randomly selecting a student and that student being a female would be 162 over 265. But ladies and gentlemen, notice there were 102 female students that responded no. So we got to subtract off this joint probability of having a female say no. That'd be 102 over 265. We got our answer, which is 169 over 265 is the probability of randomly selecting a student and then them having be a female or having responded no, as far as the adequate lighting is concerned. Does that make sense? These two different addition rules, whether the events are mutually exclusive or are not. Okay. All right. One last rule, and then we're going to wrap up the lecture of Math 130. One multiplication rule I'm going to show you. All right. To say events A and B are independent, is to say that the occurrence, or excuse me, the probability of occurrence of event A in no way affects the probability of occurrence of event B. And vice versa. That's what it means for two or more events to be independent of each other. If the occurrence of one event in no way, shape, or form affects the probability of the occurrence of some other event. Example. Event E1 is defined to be that I flip a head on my coin. Event E2 is that you flip a tail on your coin. Do you agree these events are independent of each other? It's kind of like what happens on my coin stays on my coin, ladies and gentlemen, and what happens on your coin stays on your coin. These coins have no knowledge of each other. They could care less what happens on the other coin. They have no connection through the ether of space as to, you know, what happens on my coin is going to affect what happens on your coin. These are called independent events. Okay. All right. Independent events. Does that make sense there? Independent events. Here's another example. Suppose event A is to be that it rains on planet Venus. Event B is that it rains on planet Earth. You agree, ladies and gentlemen, for all practical purposes, these events are independent of one another? What happens on Venus probably stays on Venus, and that's probably a good thing. And what happens on Earth stays on Earth. Okay, these are independent events. All right. Okay. These are independent events here. All right. Suppose that we do have two independent events. So if events A and B are independent, then to compute the probability of A and B occurring, okay, is to compute the probability of the intersection of the ways in which they can occur. And this then would lead us to our multiplication rule, which is to say that this would be equal to the probability of event A occurring times the probability of event B occurring. But the events have to be independent of one another. Now, we're not going to go over the multiplication rule where the events are dependent upon one another, where they're not independent. In such a situation, you would have to speak in terms of what's called a conditional probability. You will look at that rule in Math 150 here at Mod, Probability and Statistics. Okay, so we're going to stop with our multiplication rule right here. All righty. Let me show you an example of this use of this multiplication rule here. First of all, any questions about here? All right. And this example I'm going to show you has tremendous number of applications in the real world with critical systems, ladies and gentlemen. It illustrates a phenomenon known as redundancy. Okay. Suppose I have 3 alarm clocks. All the same model. So all these 3 alarm clocks are the same model. Okay. And they're all manufactured during this at the same period of time. Suppose the probability that one of these clocks fails, meaning it fails to go off when you set an alarm. Suppose the probability of one of these clocks failing is equal to, let's say, 10% chance, 0.10. I'm going to define event E1 to be that clock 1 fails. E2 to be the event that clock 2 fails. Event E3 to be that clock 3 fails. All right, ladies and gentlemen, are these events independent of one another?
Yes.
For all practical purposes, they are. I mean, you know, these clocks don't have any recollection of what's going on with any other clock, and there's no connection between them. They're independent clocks. Okay? So what would be the probability of event E1 and E2 and E3 occurring? In other words, what would be the probability that clock 1 fails and clock 2 fails and clock 3 fails? Well, since these are independent events, according to the multiplication rule, this is going to be equal to the product of the individual probabilities. So this is going to be equal to the probability that clock 1 fails times the probability clock 2 fails times the probability that clock 3 fails. Which is to say it's going to be 0.10, which is the probability that any clock fails, times itself 3 times. Which, when you take 1/10 times 1/10 times 1/10, you're going to get 1,000th, which as a decimal is going to be this right here. This illustrates something very important that's used all the time in critical systems in the real world, ladies and gentlemen. It's called the concept of redundancy. For instance, if you just had one of these alarm clocks and you had a very important, let's say, job interview the next morning and you were dead tired, all right, and you're totally zonked out, what's the probability this alarm clock's going to wake you up to get you to your job interview? There's a 10% chance that you're not going to make that job interview. All right. How can you reduce that probability of utter failure? Well, you can string together 3 of these alarm clocks. All right, wind up 3 of them and set them all for the same time. And the probability of having total utter failure, all right, where all clocks fail, your probability is driven down from 10% all the way down to 1/1000%. So you can see here, ladies and gentlemen, that by having a backup of a backup system, okay, you reduce the probability of having a total failure. And this concept is used with, like I said, critical systems. For instance, a critical system would be like a system on board an aircraft. All right. If you have a critical component, that means the difference between an aircraft, flying properly or crashing. You might want to have a backup of that system. By having a backup, maybe a backup to a backup to a backup, you can drive the probability down to a dirt low level, whereby you have, for all practical purposes, a fail-proof system. Okay. And this redundancy concept you can see in action here with the law of probability with the multiplication rule here. All right. The redundancy is used also for like data storage. If you only have, like I'm experiencing this now because I forgot to back up my hard drive on the Google Cloud. My power supply died. I think it's just my power supply. So I ordered another one. I'll put a new power supply in. Hopefully my computer fires up. I should have had a backup for my hard drive, and I will probably do that in the future, without a doubt. But it's nice to have a backup. And, they actually have backup hard drives off site too. So like if the building burns down, you still got a hard drive in another building that did not burn down. Okay. So this concept of redundancy can help immensely to reduce probabilities of critical systems, right? Using this multiplication rule of probability here. Is that making any sense there? Multiplication rule. All right, let's see. How much time do I got left here? Well, wow, I don't have that much time left. So I think that for the most part should do it, ladies and gentlemen, for the lecture portion of Math 130. Hopefully you've got something out of this course. And if you stuck with the course, I do believe you are mathematically more equipped today than you were the day you started this course. It may not feel like it, but we all have matured in this course in one way or another. I firmly believe that. And all that remains now is just the remaining assessments. Okay. And like I said, in 2 days, I will release the Chapter 8 exam. I also try to post a preview of that exam on Canvas and see if I can write the solutions out to that thing and get them to you. I also emailed all of you a final exam preview or a review with the answers. Try to bring any questions you might have on that during our session, which will be, you can even bring questions to that in 2 days if you want, or you can wait till next Monday if you want to do that. Okay. Or even Wednesday of next week as we wrap up the online session of this course. All right, so I'm going to let you go. Have a good day. I believe I'm going to open up the Chapter 8 quiz, and I will also indicate via email the due dates for these things, the Chapter 8 quiz, Chapter 8 exam, and then the final exam. So make sure you always check your emails. All right, have a good day. I'll stay on the line for a couple minutes.